Chapter 11, section 11.1. Goodness of the fit. Goodness of the fit remained that sample data consists of the observed frequency count arranged in a single row or column. We call it one-way frequency with some particular distributions. So here, as we go through the example, then you understand it better. But there are some letters that we use: O, E, K, and P. And mainly O is observed frequency, E is expected frequency. K is represent the number of different category or cells. N represent the total number of trials. And the letter P represent the probability. One of the conditions in this section is you want to make sure that expected frequency is at least 5. So it always has to be equal to greater than 5. And for null and alternate hypothesis, we basically use the same for all of them. That null hypothesis is the frequency can't agree with the claimed distributions. And alternate hypothesis is the frequency count do not agree. This is the formula we use for statistic, test of statistic. And we are using table A4. And for table A4, you are using K minus 1, the number of category minus 1. So here is 2 examples that if the expected frequency are all equal, in the calculation we use N divided by K. And if expected frequency are not all equal, then we are using N times P, which on the next example, you see that for Bedford, we are using this formula for Bedford law. Example 1, see, a simple die is rolled 45 times. So when you roll 45 times, we observe that, every dice has 6 faces, right? We observe that number 1, it shows 13 times. Number 2 shows 6 times, 3, 12, 4, 9, 5, 3, and 6, 2 times. So when you add all these numbers, it's 45. So when you roll the die 45 times, 13 times you see number 1 and so on. These are observed frequency. How do I calculate expected frequency? Expected frequency is, if expected frequency all are equal, then is N divided by K. How many categories do we have? 1, 2, 3, 4, 5, 6 categories. So, and how many times we roll the dice? 45 times. So expected frequency is 45 divided by 6, or 7.5. Another example is like Bedford law. He claimed that it's not always the same. Expected frequency is like here in this one. Using the same result from part A, suppose that we claim that instead of being fair, the die is loaded so that the outcome of 1 occurs 50%. So let's say we load the dice is loaded, and we claim, no, it's not that the expected frequency is always the same. No, it's 50% or 0.5 of the total is expected frequency. All right. So we are saying that if you take 50% or 0.5 times 45, 22.5 is expected frequency. Or they will claim that for the rest of them is 10%. 10% of the total is your expected frequency. So if you take 10%, which is 0.1, and multiply by 45, we claim that expected frequency for the rest is 4.5. So this is an example that expected frequency is not the same. It's just the percentage. So we have one of these 2 categories. And again, this is a formula they use for test of statistics that I show you in the examples. So in the example here, a random sample of 100 weight of the California is obtained. So 100 people, their weight is measured, and the last digit of those are summarized before. So people who last digit of their weight is 0, we counted 46. People whose last digit of their weight is 1, 2, and so on. These are observed frequency. Okay. And how many categories do you have? 10. How many rows? 10. So that's your K. K is 10 here. All right. So here, then we in here, our HO and H1. Again, our HO is the, that all the proportions are the same. H1 is we get a proof that at least one of them is not. One of them is. So this is your HO and H1. And then we basically use for all the problems. In this one, the significant level is 0.05. So what we do is first, we want to go to table A4. You go to table A4, and table A4 we are just using for one tail, not two tails anymore. So it would be just one tails, like that. Okay, so the degree of the freedom is K minus 1 is here, and this is the alpha. So here in these examples, they're saying that you have, we calculated there were 10 category, right? So K was 10. So DF is 9, is K minus 1. So DF is K minus 1, which is 9. So DF is 9 and alpha is 0.05. So K 9 and alpha is 0.09. So K is 9 and alpha is 0.05. You get that number here. Okay, 16.91. So this is what you have on the graph. Now we want to do the calculations. So to do the calculations, you need to create a table. This table here, the observed frequency is these numbers. And we calculate that expected frequency. We want, in this example, we want to say expected frequency is always the same. Expected frequency is N divided by K. We measure weight of 100 people, and we divide it into 10 category or 10 lines here. So it would be N divided by K or 10. So we put that number here. We put that number here, 10, 10. Then we subtract O minus E, means take each of these numbers, subtract. So 46 minus 10 is 36. 1 minus 10 is -9. We raise it to power of 2, like -9 to power of 2 is 81. Then you take this O minus E to power of 2 and divide it by E, divided by that number. So 81 is 8.1, 1,296 is 129.6. At the end, when you add all these numbers, that would be your test statistic. And that's the number that we just go to the graph and see where does that fall. That number falls way on the critical area here. So in that case, we reject HO. Anytime we fall into critical zone, we reject HO. So we reject HO, and we say, no, they are not, proportions are not equal. Another one is like here, the Bedford. This chapter problem introduced Bedford law. Bedford law, where a variety of different data set include numbers with the leading digit and follow distribution in the first. He claimed that normally 30.1% are always number one when you rule a die. I mean, when you weight people. He claimed that when you weight people, the last digit of their weight, 31.1% of the total is always 1, 17.6% is 2. So what I do is, we measure 271. We measure weight of 271 people, right? So Bedford claimed that out of these 271, 30.1% of them, if you take 30.1% of this number, that would be your expected frequency. Or if you take 17.6% of this number, that would be digit 2. Or for digit 3, if you take 12.5% of that, would be digit 3. Okay, and he just showed a couple of them here because it takes a long time to do the calculation. See, so he claimed people who last digit is 1, you got to take 30.1 or 0.301 of 271. That is the expected value, 81.57. Excuse me. and so on. So, and then I'll show you an example of the Bedford that you understand. All right. So, with all this, here are some examples. I'll put the answer here. I'll probably make a copy of this and put it online so you could actually see it. And then, and then I'll let's go to the page that I actually did. This problem's number 4. I did that problem for you. Conduct a hypothesis test and provide a test statistic and a critical value. All right. A person drilled a hole in a die and filled it with a lead weight, and he processed it 200 times. So your N is 200. And these are for every number, these are the frequency. Okay. And now they ask us to calculate the test statistic, the critical value, stuff like that. As far as finding the number, I put I listed all here. So so what I do, I have the observed frequency 25. Let me get all of 25, 27, 44, 38, 29. The frequency, how do we calculate the frequency? We did it 200 times. That would be your N. And there are 6 categories. See, 1, 2, 3, 4, 5, 6 categories. So E is N divided by K, which is this, which is 3.33. So what you could do, if you want to use the calculator, let's say they ask you to find all these numbers. In your calculator, you put all these numbers in L1, these numbers in L2, and then you have to subtract. I think I might have those here. See here, I'll put the numbers here. Now, if I actually want to find the numbers and fill in information here, let's say you want to actually get all the numbers here. In this one, it said O minus B, means you take the numbers and subtract. So it would be 25 minus 30.3. So here, if you want to do that, you go to L3. This is L3. And you put L1 second, L1 minus second L2. See? That gives you the difference. You see the first one is minus 8.33. So what it is 25 minus 33.33, which is minus 8.33. That's how you got that number to the calculator. So you take all these numbers and you list it here. Now, the next one is, it asks you to take this column and raise it to power of 2. So in that case, you go to L4, you always have to go all the way to the top. L4 is what? L4 is L3 times L3, or L3 to power of 2, right? So it would be second L3, and then multiply, again, L3, or L3 to power of 2. That would be a number here, okay? So these are the numbers that you list here. Then the last column is, they are saying, take this L4, take L4 and divide it by E, which is L2, okay? So for that one, we have to take L3, divide that by L2. That gives you all the numbers that you need here. And remember, the formula is X2 is sum of O minus E to power of 2 divided by E. This is what we need. This is a statistic. That means you have to find all the numbers in L5. You have to add all these numbers together. If you want to do that, you could either do the hand calculations, or you could just go to Stat, Calculations, the very first one. Everything was in L5. I think it's already there, L5. I don't know why, but. So the sum is 6.0. So let's keep that number in mind. 6 point, and then times 10 to power of -4. Anyway, now I want to do the calculation without going through all this, okay? So for that, you go to Stat, Test, and then X2GO. First, we have to put everything in L1 and L2. So what I have here is, I actually need just L1 and L2. So I don't need the rest. So if you want to use your calculator first, you got to put all these numbers in L1 and these numbers in L2. You just need L1 and L2, okay? Then you go to Stat, and then you go to Test. GOF test. You see all these L1, L2, DF is 5. I understand DF is 5 because you have K6, 1, 2, 3, 4, 5. So you have 6 rows. So DF is 5. All right, so let's see how it comes up. So they tell you that X3 is 8.32. So it's kind of different when you did the hand calculation. So this is the exact one. So X2 is 8.32. The p-value is 0.139. Now, remember this 8.32, it doesn't fall into the critical area. In that case, we have to accept HO. We do not reject HO. And also to double check on that, if your p-value is greater than alpha, also we have to accept HO, or we should not reject HO. See, there are 2 ways to prove it. One is if your p-value, which you calculate in the problems, in 1.139, if that number is greater than alpha, which is given in the problem was 5%, was 0.025%, then that, say, alpha was 0.025. So if it's greater than that, or if it doesn't fall into the critical area, then you do not reject HO. And then there is another example here. I think it shows number 6. See, number 6 is very similar to the Bedford law. Here, they're telling you the table below lists the number of games played in a yearly best of 7 baseball championship series, along with expected proportion. So actual numbers are given. These are the observed one. But for the expected one, they're saying you take 2.16 of each. Okay? So these are the observed. Observed values are these. 16, 19, 23, 39. These are the observed value. But to find the expected frequency, some of these numbers is 97. I'll show it to you. So to find the expected frequency, they are saying take 2 divided by 6. Take this portion of the total. That means take 2.16 and multiply that by 97. That 12.13 is your expected frequency. Or take 4/16 and multiply by that. That gives you the second one. and like that. So that's how to calculate your expected frequency if the percentage is given in the problems. Okay, so you could either do it this way, which do not recommend, or you go to the calculator, you put L1 and L2, very similar to the other one. When you put L1 and L2, L1 is your observed ones, L1 is these numbers, and this is your L2, O and E. And then you go to X2 GOF test. DF is 3. Why? Because K is what? 1, 2, 3, 4. K is 4. So we should basically use K here. Don't mix it up with N. K. DF is always K minus 1. Okay. So when you do that, then you see that your p-value turned to be 0.085, which is greater than 0.05. So we do not reject HO. And X2 from the calculator is 6.629. Now, how do I calculate the one for the graph? The graph alpha is given in the problem. Let's see what the given alpha. Alpha is 0.05. Okay. And DF is K minus 1, which is 3. So you go to 3 and 0.05, 3 and 0.05. You find that number. See, K is 3. I mean, DF is K minus 1. K was 4. DF is 3. And this is 0.05. That's your number, 78.15. That's the number you put here. And this number that we find here, which is 6.6, is falling here. It doesn't fall into the critical area. All right. And these are some multiple choice. And here is, again, it show you how to do this kind of calculations. Okay, so that would be section 11.1. And again, I'll put a copy of this online.